and then at 2000 RPMs, we kind of have the frequencies shift downwards, right? That I wasn't expecting that. I thought the spikes would just get lower, like the number of samples would get less and less. Welcome to episode 5. The whole point of this project is to turn my super ear toy into an ultrasonic diagnostic device. However, we're not there yet. We still need to upgrade our consumer mics to MEMS ultrasonic microphones. However, even at this stage, I want to show to you that even with consumer mics, this is still a valuable diagnostic tool. In today's episode, we're working on my 2001 Toyota Corolla. I highly suspect there's a vacuum leak at idle. We are going to cross-reference OBD2 long-term flow trim data along with this frequency spectrum that we get using our analysis scripts from the last few episodes in this series. And we are going to see if that 11,000 hertz spike decreases down, as well as if their long-term flow trims also decrease when RPMs increase. So let's get started. Set up here. Okay, good. Turn that on. Have it kind of sit kind of in this area right here. Right here. Okay. Oh! Laptop's gonna die pretty soon. Turn the AC off. Okay, just idle. Idle. Let's go ahead and start recording that one. Okay. Long-term flow trims, idle, 2,000 RPMs, 4,000 RPMs, and then the 11,000 spike. Let's see. No codes. Can you believe that? This old-ass car, no codes. Okay, we just want to see. Of course, it would be smart to let the engine warm up a bit, but let's just go ahead and we'll just collect the data. We have at idle, we have 8.6 positive %. Let's go stop the recording. export. Okay, finished. Now we'll delete. Okay. I need to go ahead and I'm going to start recording 2000 RPMs. Actually back down to 8.6 actually, same. Okay. So here's idle, and here's the frequency spectrum for idle. Here's 2000 RPMs. Okay, let me get 4000 RPMs over here, and then get his frequency 2. There we go. Okay, top row we have time domain, time on x-axis, amplitude on y. I don't even know what amplitude unit is. We should probably do like a log thing here, like decibels. That's probably be the way to do it. Our main concern is frequency spectrum. And this is why I did not expect. So at idle we had a huge spike around 23 kilohertz. Absolutely giant. And we had some more spikes here. 16 kilohertz and 13 kilohertz. And then at 2000 RPMs, we kind of have the frequencies shift downwards, right? That I wasn't expecting that. I thought the spikes would just get lower, like the number of samples would get less and less. I wasn't expecting the actual frequencies to get lower. So here's 15 kilohertz is our large spike. It was like, it's like 22, 23 kilohertz at idle, and then it went down to 15 kilohertz at 2000 RPMs. And then when you look at 4000 RPMs, that huge spike goes down to, looks like 4.8 kilohertz. And yeah, so we are seeing an engineering principle in action. And this is based on the vacuum of the engine. So at idle, you have a very high negative vacuum. The higher you get up in RPMs, the more closer to atmospheric pressure you get to the 0 psi. And if you're boosted, if you have a turbo, you're actually going above atmospheric pressure to get positive pressure. So let's go through the response from AI and the prompt that I made. The prompt is very important, by the way. Gotta get the prompt correct. This is the most important part of using AI. So I sent it a screenshot of all the graphs, and this is my prompt. You are an acoustic harmonics engineer working for Boss or Yamaha. The graphs on left side are 600 RPMs, the middle are around 2000 RPMs, and the right side are 4000 RPMs. The top row of the graphs are time domain wave, while the bottom are spectrum analysis by fast Fourier transfer. Fast Fourier transform. My long-term foil trims from left to right, and this is what we got from the ODB device that I had connected to the car. So at idle we had 8.6 positive percent. That means it's running lean, it's adding gas to the mixture. After warming up, it actually went up to more. It went to 11.2 positive percent. And at 2000 RPMs, it was the same 8.6% positive. This is the smoking gun right here. At 4000 RPMs, it went down to 6.3 positive RPMs. That's the smoking gun because we know we have a vacuum leak somewhere. At higher RPMs, vacuum leaks do not affect things as much. So you'll get closer to a zero trim, where you don't have to, the computer doesn't have to add any gasoline to the mixture. Anyway, enough of the mechanic knowledge. Let's move on. We see that long-term foil trims go down as RPM increase, which would indicate a vacuum leak. However, we used to have an 11,000 Hertz spike at idle. Now it seems the spike is changing its frequency to lower frequencies as RPM increases. I was expecting the amplitude or the number of frequency samples to decrease as the RPM increases. Am I missing something, or am I not understanding a prime principle? Explain this data to me. I'm also only 12 years old. Huge thing right here. Huge thing. You do not want it to use like sophisticated language. You want it to keep the language very, very simple. And then right here in the very beginning, you want to do the identity. You want to tell AI what row it's playing, so it doesn't give you a generic answer. Okay. It says that this is impressive work for a 12-year-old. Like, if you're 12 years old and you're doing this stuff, then you have a very bright future ahead of you. Yeah, really, like, my gosh. But anyway, so the mystery of the spiking shift. So at idle, it shifts a higher hertz, goes down to lower frequencies as RPM goes up. So the spike isn't caused by spinning metal parts, but by air resonance, right? And it explains the soda bottle effect, the Helmholtz resonance. Think about blowing across the top of a glass bottle. It makes a specific note. If you change the size of that bottle or the speed of the air moving past the opening, the note changes. So the vacuum leak. If you have a vacuum leak, you have a tiny hole where air is being sucked in at 600 RPMs. The engine vacuum is very high. suction is strongest. Negative PSI. If you're doing Honda tuning, this will kind of be the most left side of your foil map if you're using the map sensor, right? So you'll be like in the negative PSIs for your pressure, for your map manifold absolute pressure. So it's pulling air through that tiny hole very fast, creating a high-pitched whistle noise. Why it drops as you open the throttle to hit 2000 or 4000 RPMs, the suction manifold vacuum actually decreases. So it gets closer to zero, to absolute, to atmospheric pressure. The same pressure that's basically outside of your car in the atmosphere. Close to 0 psi, right? Because there's less pressure difference, the air doesn't whistle through that leak as sharply. So it actually, the resonant frequency will slide downwards. Okay, so yeah, that's the big thing right there. And then it also talks about the noise floor. At 4000 RPMs, your spectrum bottom right, the floor of the graph, the fuzzy blue part at the bottom is much higher than at idle. This is called the noise floor. It's louder, like it's louder. You're revving up the motor and everything is louder, right? So, connecting the dots, it says that the long-term foil trim numbers on the smoking gun for the vacuum leak. Right. As the engine is gulping more air, the legal air through the main throttle, that the illegal air, the tiny leak, doesn't matter as much. So it has to only add 6.3% more foil compared to at idle it had to add in 11.2% more foil. And now I kind of did this, so mostly vacuum that's causing the tone to change. At idle we have more samples at higher frequencies than at higher RPM levels. And yes, there's a resonant, the pressure dependent resonance. Okay, so there we go. That's what's happening. And this is why we are doing this, because we're learning prime engineering principles, using this, collecting real data, and solving real issues. Next, we're going to add the ultrasonic MEMS microphones so that we can open up the frequency range and we can pick up more higher frequencies over here. We might even have to increase our sampling rate too, from, well, right now we're at 192 kilohertz. Might have to increase that. And then also I think we need to add some type of filter. It is very, very noisy data. Very noisy, like it just picks up everything, right? So that will be in the next episode. I gotta find a MEMS microphone that has through the hole pins, which I can't find. So we might have to do surface mount one and solder legs to it. Until then, thank you for watching and have a nice day.